Hello and welcome to Remcom's webinar on detailed indoor channel modeling with diffuse scattering for 5G millimeter wave wireless networks. I'm Greg Skidmore, the Director of Propagation Software Modeling Tools at Remcom, and in today's webinar I'm going to demonstrate a new capability that we've developed for our Wireless InSite product as one of several new features that we've added to support new development for 4G and 5G data networks. So the objective of our webinar is to use Wireless InSite's new diffuse scattering capability to demonstrate how this capability affects millimeter wave channels. Our agenda will include going over the diffuse scattering model and its concepts behind the development of the model, setting up a millimeter wave indoor scenario based on an IEEE paper that we have replicated, defining materials with diffuse scattering, and setting simulations up so that we can use diffuse scattering within the simulations. And we'll conclude by viewing and analyzing some of the simulation results from this capability and looking at how they've affected the outcome. We expect this to take approximately 30 minutes, and we'll hold for a few minutes afterwards for questions and answers. Now, during the webinar, you can ask questions, and we'll have staff who are moderating and available to try to address these through the panel on the webinar shown here in the figure. And for your convenience, you can also undock this question panel and expand it and do other things to make it easier perhaps to use. So to start with, why a millimeter wave and why the interest in addressing millimeter wave in our Wireless InSite product? So as many of you probably know, 5G is going to be addressing some expected growth over the next decade with perhaps 10 to 100 times more connected devices, 10 to 100 times higher data rates for each of these devices. We may see perhaps an overall increase of 1,000 times of the required data demand. Millimeter wave is one of the many solutions that are being planned, among many other things. And one of the reasons is that it adds significant new spectrum and the potential for higher bandwidths. So to model this in a tool like Wireless InSite, there are a number of key features that need to be included. Atmospheric absorption loss is very significant at certain frequencies. Highly directional antennas are even more important as you get up to millimeter wave frequencies where the beams can be very narrow. Arrays and MIMO systems are obviously becoming a big part of 5G as well, so being able to handle this and handle this for millimeter wave is a key feature. And handling the details of polarization and phase become even more important when we move up to frequencies where the wavelength is just a few millimeters in size. So the last item is something that is coming soon that we have a development version of that we've completed, and it's diffuse scattering, which is the subject of our talk today. And as you can see over in the pictures to the right, there are a number of things that Wireless InSite can be used for indoor, outdoor, macro cells, small cells, indoor Wi-Fi scenarios. So the diffuse scattering model that we've developed for Wireless InSite was based on a model described by Degli Esposti in a couple of references that we'll show later in this talk. We've extended it with a third reference that describes the cross-polarization effects on scattering, and we've added options to include phase so that we can support complex antenna systems, arrays, or MIMO for 5G and other applications. For each material, the user can define how the scattering occurs on that material by selecting from 3 different models and parameters that are associated with those models. The 3 models are Lambertian, Directive, or Directive with Backscatter. And the parameters just define how directive they'll be, how strong the scattering is, and other properties that we'll describe. The first model is the Lambertian model. And the Lambertian model has a scattering pattern that centers around the normal to the wall, regardless of the direction that the field was incident to that wall. It's defined by a scattering factor between a value of 0 or 1 that defines how much of the field scatters away from the wall as opposed to reflecting in the normal specular direction. And it also has a cross-polarization fraction that defines how much of that scattered energy is scattered in the co-polarized direction as opposed to the cross-polarized direction. The second model is called the Directive model. The Directive model scatters generally in the direction that a reflection would have occurred, but it spreads out significantly around that direction. In addition to the two parameters that I described for the Lambertian model, it has a third parameter called alpha that is simply a term, a value between 1 and 10 that feeds into the formulas and defines how narrow or broad this scattering beam will be. And the third model is a directive model with backscatter, shown at green in the diagram to the left. In this model, there's still a forward directive beam that follows the reflection direction, but it is added to by a backscatter beam that goes in the backward direction. This might be the type of scattering that one would see if there are lots of right angles, and some of them may effectively be corner reflectors that scatter energy very strongly back toward the transmitter. So this adds two additional parameters, beta, which is another term between 1 and 10 that determines how strong that backscatter is going to be, and a fifth parameter, lambda, that is a fraction that describes how much of the energy scatters in the forward direction as opposed to the backscatter direction. Touching a little bit more on those parameters, alpha and beta for the beams, we show some plots here that show just how the pattern changes as you change the alpha and beta parameters. On the left, we have the directive model. As you go from an alpha of 1 in red to 4 in magenta or to 10 in the light blue, you can see it becomes more directive in the forward direction and the beam becomes stronger and narrower. In the backscatter case, we see a similar effect, but if alpha and beta are changed together, as we progress to the higher values, we can clearly start to make out strong forward and backward lobes, and at the lower values, they start to smear together. In this plot shown here, we use the default lambda value from Wireless InSite of 0.75, which indicates that 75% of the power scattered is scattering in the forward direction and 25% in the rear. When a surface has diffuse scattering associated with it, the model will break down the facets on that wall and calculate a large number of paths to each of the small subfacets of the wall. In this example, we show what the paths under the hood would look like. It performs a surface integration and finds contributions from each of these many paths. Those contributions are all verified to make sure that there's no shadowing or that the other multipath effects will work to each of the points on the walls. And then these are combined and become aggregate paths that get passed on to the outputs of the simulation. So in a wireless simulation, you would receive two aggregate paths as shown here that are power weighted to where the center of all these many paths, the power weighted center, occurred. Diffuse scattering paths can also incur multipath and happen along multiple interactions in a series of paths between a transmitter and a receiver. On the right, we show an example with two reflections, a diffraction, a third reflection, and another diffraction between a transmitting and receiving point. At any point along this wall, diffuse scattering might occur. So a similar series of paths can be created that are scattering at different points along the wall, and these create additional contributions of scattered energy with all of their terms that can make it to the receiver. Now, it's also important to know that every time these diffuse scattering interactions occur, these paths can also scatter in many other directions. For example, we talked about the directive with backscatter. We might see some of these paths scatter right back in the direction toward the transmitter or further down to the street to other sensors and receivers that are in the scene. So in total, the diffuse scattering can add a large number of additional paths to the calculations. The outputs from the simulations include path data, just like we have for our interactions that reflect and diffract normally. We can also have interactions that scatter, and these generate additional paths. The path data that we receive shows interactions with structures, the time of arrival of those paths, directions of arrival and departure, and all of this can be used in a type of output called a complex impulse response to look at the arrival of copies of the signal and the time at which they arrive. There are also some new outputs associated with received power. So the total received power is modified when we turn on diffuse scattering. We can also break that down and look at the specular power, the amount of power that's received if we ignore all the diffuse scattered paths, the diffuse scattered power, absent any of the specular paths, and then the total when these are summed together. There are two different types of total power outputs. One assumes that the diffuse power is incoherent, that it's lost its phase information, and so that it adds more like a power sum, similar to how one might add a white noise. And a second assumes that they are summed coherently and that they retain some of their phase coherence. One of the reasons that we've kept this second type of summation is that when we're dealing with scattering that's hitting an array of tightly spaced antennas in perhaps a MIMO system, understanding how that phase is shifting as you sweep across the array becomes extremely important. So we've gone to great lengths to make sure that we can handle those kinds of conditions. There are also derived outputs, things like path loss and gain, that incorporate the effects of the diffuse scattered power when diffuse scattering is included in a simulation. There are many advantages to the approach that we've done in our model here. One is the ability to scatter from any interaction along a ray path. Compared to some other approaches, this appears to be fairly unique. It can allow us to have scattering at the beginning or at the end of a path. We also verify all of the small subpaths that we showed in the diagram a few slides back to make sure that all of those paths are valid and to make sure that the scattering is properly accounting for shadowing and other effects across the surfaces. This improves our accuracy. We also can scatter in all directions. There are some optimizations that some might want to apply that would restrict where the scattering can occur, and we have not applied these. We can scatter in any directions and then apply the scattering beams to all of those directions, again, to try to ensure that we include the most accuracy in our simulations. And finally, the handling of polarization and phase supports MIMO and antenna arrays, which are becoming increasingly important. So now I'd like to go through a demonstration of diffuse scattering for an indoor scenario shown in the diagram here for a series of receivers and a transmitter in which we've tried to replicate an IEEE paper. On the right, we see a picture of the floor plan from the IEEE paper, which we have used with permission from IEEE, and the reference to the paper is shown below. We focused our simulations on the first transmitter called TX1 and the 9 receivers that this transmitter has transmitted to. This includes 7 receivers that are in a room fairly close to the transmitter, some in line of sight and some blocked by cubicle walls. And it also includes 2 receivers down the hallway and around the corner, labeled 8 and 9. Here we see a diagram when we have built our floor plan and placed transmitters and receivers, and we'll go into more detail on each of these in a moment. The primary construction in this floor plan includes drywall, cubicles, desks, cabinets, and a number of other features. To choose materials for all these structures, we used an ITU reference that provided estimates for drywall, concrete for the ceiling and floor, and glass windows. We used some other parameters for chipboard based on an ITU recommendation. And for the cubicle walls, we found some values assuming a fiber reinforced plastic honeycomb core based on some of the material that we've been able to research on the type of internal structure of cubicle walls. We then did our simulation comparing the Lambertian and Directive models. We found the best agreement with the Directive model, and so that's the one that we're going to show in our demonstration today. And we specified scattering factors for all these materials between about a factor of 0.2 and a factor of 0.5 for the walls, cabinets, ceilings, cube walls, depending on how rough those materials were. All of this was fairly consistent with another reference that we found where measurements were taken to predict what these values should be at 60 gigahertz. So in a Wireless InSite project, shown here in the graphical interface, one of the first steps to building one of these types of scenarios is to load in the floor plan image, as we show here. Once we have a floor plan image, we can build up the floor plan on top of it. There are mechanisms in Wireless InSite where we can drag and draw walls on top of the floor plan, specify the materials for the ceiling, floor, and the walls, and insert windows and doorways as well. Once this has been built, we can call out some specific structures such as the support columns and identify additional special materials as we see fit to help build up our structure. In this scenario, we focused around this main room around the transmitter and the room next down the hallway where the second receivers number 8 and 9 were. So we focused our construction of the walls, and then the next step was to look at the furniture that was placed within this structure. And we built this in as well. So in building furniture, most of these materials, several of these cabinets and file cabinets, we looked at the floor plan and we drew these using a simple tracing and extrusion function that Wireless InSite has built in that allows us to build up metal structures to represent the cabinets and the file drawers. For the more complicated pieces of furniture, we used CAD models that were available online, and we used external tools to simplify these down, and then we could place them, rotate them, and size them to fit, again, on top of the floor plan, which you can see below. The next step is to define the materials for each of these different structures in the floor plan and for the furniture as well. We defined materials that represented what they were made of. So I'll touch on a couple of these just as examples. The drywall, for this, as I mentioned earlier, we used an ITU recommendation to specify the materials for conductivity and permittivity. The thickness we assumed to be 1/2 inch, and we used a layered dielectric that allowed us to have 2 sheets of drywall separated by a gap of air to represent the air in the studs between the sheets. We then defined the properties for diffuse scattering. We used the Directive model. We set the scattering factor to 0.2, which allows for some scattering. At this frequency, at 73.5 gigahertz, this might represent a textured wall paint, but a fairly smooth surface. And we left the other 2 parameters at their defaults, a cross-polarization fraction that indicated that 40% of the field would be cross-polarized once scattered, and an alpha value that was a medium value of 4 for the amount of directivity. There are also some advanced parameters, and we left these in their defaults, including this subdivision of facets that allows it to calculate all of the small facet paths, as I showed earlier in the presentation. Another one of the interesting materials was the cubical partitions. For these, we used parameters for a fiber-reinforced plastic based on some online data. We assumed 1 3/4 inch thickness, and we had to extrapolate from some lower frequency measurements that had been taken in the past. For the diffuse scattering materials, we again used the Directive model, and this time we set the scattering factor a little bit higher to a value of 0.5. This indicates that 50% of the field that impinges on this wall is going to scatter diffusely rather than reflect in the normal specular directions. And we again left the cross-polarization at 40% and the directivity using a medium level defined through the alpha parameter 4. Our reason for putting a stronger scattering factor on the cubicle walls is that in our research into the construction of cube walls, we saw that some of them are constructed of a fiber reinforced plastic honeycomb, which has a lot of gaps and shapes to it. And if this is the main interaction that the electromagnetic waves will have, we expect that this would scatter quite strongly. A value of 0.5 would be similar to what you might see from a concrete wall, or perhaps from something like a ceiling tile with the holes and gaps. That might also create a factor about this level for a frequency as high as 73 gigahertz. Next, we began to define our measurement equipment. We set our waveform for the frequency at 73.5 gigahertz to replicate the study. And then we defined 3 different antennas. The first was a standard gain horn. We used parameters for the standard gain horn that were based on, after looking at several different gain horns for this frequency range, we chose the one that gave us the gain and the beam width parameters closest to the paper. And so this gave us a pattern with a main lobe with about 15 degrees beam width as indicated in the paper, and we set our gain at 20 dBi. Next, we defined 2 omnidirectional antennas, one vertically polarized and one horizontally polarized. And we place these in the 9 positions shown in the paper. The 7 are shown here, and if we zoom out a little bit, we can see down the hall where the 8th and 9th receivers are. The last step before running our simulations was to look at the properties for the simulations. So for the transmitters and receivers in the main room, we used 3 reflections, 1 transmission, and 1 diffraction. These are settings that indicate how many interactions paths will be allowed to have in the simulation. After running many simulations, we found that this was sufficient to pick up the multipath, the dominant multipath that we would see within this room. And we also did a second set of simulations with the same settings where we also enabled diffuse scattering. The diffuse scattering properties for the area in the room, we chose maximum reflections of 1 reflection and 1 diffraction, and we allowed this to happen, these diffuse scattering interactions to happen anywhere along these paths. And again, these settings were chosen because we found that within this room those settings were sufficient to capture the top 25 or 30 dB of paths that were being received at the receivers. For the transmitters to the receivers down the hallway, we used some additional interactions. Because those receivers were far down the hall, we included the allowance for up to 2 transmissions so that signals could actually go through 2 walls, through one of these front offices, for example, to get down the hallway. And we added some additional reflections as well. And likewise for the diffuse scattering, we enabled diffuse scattering for the diffuse scattering version of the simulations. And we added the ability to do up to 3 reflections and then a diffuse scattering interaction, as well as 2 transmissions and a diffraction, so that the paths would be able to get down the hallways to where those receivers were and then scatter. As an additional optimization, Wireless InSite offers the option to check a flag that allows you to limit the diffuse scattering to just the last interaction before hitting the receiver. And so we chose this in this case as well to help with our simulation. One last factor of note is that in the paper, the measurements were performed by actually pointing the antenna directly at each of the receivers. So to replicate the measurements that were taken on the paper, we had to do the same thing. So for each receiver, we actually had a matched transmitter-receiver pair with the transmitter pointing at the receiver, and the receiver was then modeled as an omnidirectional antenna. In the paper, they used directed antennas, but they rotated them around and collected measurements at several different sweeps of angles to replicate an omnidirectional antenna. So this was the best representation of the final data that were collected in the paper. We then ran the simulations, and for these simulations and settings, each of the point-to-point simulations from one transmitter and the co-pol and cross-pol pairs ran for just a couple of minutes for the specular simulations. And when we turned on diffuse scattering, for the ones in the room, they ran for about 7 minutes, and the ones down the hall ran for about 15 minutes each for each receiver. So one of the first things that we might want to look at from these simulations is a series of paths to see where the paths propagate and what the multipath looks like. So going from the transmitter to the 4th receiver shown here, this display is showing all of the multiple paths in the top 100 paths that were calculated from this transmitter to this receiver. We can see that there's a great deal of multipath within this room, and that there are lots of paths that are going off to the side outside of the main beam, and so their power is a little bit lower. The paths in the reds, oranges, and yellows are the stronger power, and the paths in the blues are the weaker power, moving outside of the beam. Now what we notice when we then look at the results from the diffuse scattered simulations is that we still have some dominant paths in red and orange that you can see very close to the middle here along the line of sight, But we have a larger number now of paths in the yellows and greens that are scattering within the main beam and off of many of the structures that are right around the receiver within this office building. So physically, this shows an idea of how the diffuse scattering has changed where the top 100 paths are happening. Another way to look at this same information is to look at the complex impulse response. So the complex impulse response plots each of those points of received power as a function of the time of arrival. So looking at these 100 paths a different way, in blue we see the paths from the specular simulation, and in red we see the paths from the top 100 when we turned on the diffuse scattering. One of the things that we notice here is that in the specular simulation there are a few key points where interactions are occurring in the multipath that are dominating the rest. And in the diffuse scattered simulations, there's a little bit more of a smearing, many dB down, but a larger number that are coming in to the results of the measurements. So this plot shows the co-polarized measurements. We see a more dramatic effect when we look at the cross-polarized measurements. So in this case, once again, we have the blue for the complex impulse response before diffuse scattering was turned on. And for the co-polarized complex impulse response after diffuse scattering, we see the results in red. Once again, we see a wider spreading of the received power. And in this case, this wider spread is just 10 or 15 dB down below some of the peaks. And perhaps more importantly, the peak values, many of the top received power in the peak values are much higher than the received power before diffuse scattering was on. So the diffuse scattering has definitely had a very important effect in the cross-polarized results. And in this particular case, the RMS delay spread has increased from about 1.3 nanoseconds to 6.4. So in the cross-polarized case, it's changed significantly. So looking at the results, in terms of received power overall, we extracted the data from all of these different simulations from each of the 9 transmitter orientations pointing to each of the co-polarized and cross-polarized receivers at the 9 locations. And we compared what we calculated to what was measured in the paper. In blue, we see the measured data from the IEEE paper. And in green, we see the simulated results from Wireless InSite. On the left, we have the results before diffuse scattering, and we see an RMS error of approximately 3.15 dB. And on the right, we see the co-polarized results after diffuse scattering, and we see approximately the same error. What this is showing is that the diffuse scattering has not had a very strong effect on the co-polarized terms. But this is also showing that we've been able to do a fairly good job of predicting the received power for these specific cases in the paper for millimeter wave. Next, if we look at the cross-polarized results, we can see a very strong effect from the diffuse scattering. On the left, we have the case without diffuse scattering. Blue is the measured data once again, and green is the simulated data. And one thing you'll notice as well is in the measurements, they were not able to measure the results at the 8th and 9th receiver because the loss was too great. We can simulate them, but you can see that the much higher loss is consistent with the inability to measure these with the measurement equipment. So in the case before diffuse scattering, we see an error of almost 28 dB RMS error. Once we turned on the diffuse scattering, this error dropped dramatically to about 3.45 dB. So in the cross-polarized case, the diffuse scattering proved to be a very critical component of the received power. This completes our demonstration of the Wireless InSite diffuse scattering capability. In the webinar, we've described our new diffuse scattering model. We've demonstrated how to set up a millimeter wave scenario, and we've tried to replicate a measurement campaign in an IEEE paper. In the process of doing that, we showed how to define the materials so that we could include diffuse scattering in the simulations, and how to set up the simulations to enable diffuse scattering on the simulations as a whole. At the end, we presented the results demonstrating the value of doing simulations in general, but also demonstrating how important diffuse scattering was in this case for a millimeter wave cross-polarized measurement. We thank you for your attendance today. We hope that you found this useful. If you have any further questions, please feel free to contact us at the phone number or the email shown here, sales@remcom.com. Thank you very much for your time today.